Well, thank you. Thanks the organizers for this invitation. It's nice to be here, as always. Everything I'm going to talk about is joint work with Charles Tresser, and I should apologize for the date. I had a problem with my computer, and I'm using like an older, slightly older version of the same talk I had prepared. Okay. So, and in fact, it was for a talk I gave in New York, and it's longer, so I'll have to skip a few slides. Okay. So I hope nobody minds that. So the problem I'm going to talk about is the motivation is a problem in number theory, and it's been open for like 40 years, and it seems very inconsequential. In fact, it was published in a place called Journal of Recreational Mathematics, okay, by this guy Sloane. For those of you who don't know, this guy Sloane is a guy who works in computational number theory, and he's probably more famous for creating something called the Encyclopedia of Integer Sequences. I don't know if anyone has seen that. It took me a while to appreciate that. Today it's something you go online, there's a website, and you type in your favorite string of integers, and the program will spit out all known sequences of integers that have that particular string as a substring. Okay? So I used to make fun of that because I said, you know, this guy is going to write a sequel to this volume. It's going to be called the Encyclopedia of Integer Subsequences. And it will have like uncountably many volumes, and you will have a guaranteed future. But, you know, eventually I learned to appreciate that. It's useful. It's very useful. So in 1973, this guy Sloane formulated a problem which is called the persistence problem. His formulation was originally in base 10, but you can do it in any base. So what is this problem? The problem consists in taking a base, you fix a base, let me call it Q, and you take a natural number and you write this number in base Q, so you have an expansion like that where the dj's are digits from 0 to Q minus 1. And what you do is you multiply the digits together. So you take the product of all the digits. Okay, so you get a new natural number. Okay? So that sets up a map from the non-negative integers to themselves, and this map can be iterated. Now, as anybody here knows, I mean, dynamical systems on the integers are not very interesting. So that's not quite the question you want to ask. You don't really want to understand the orbit structure, so to speak, but you want to understand something about how many steps it takes for this process to stabilize. Because if you take a natural number that is greater than or equal to Q, which is the base, then it will be written as at least 2 digits in the base Q. So when you multiply the digits, you get some number which is strictly smaller than you had. So if you look at the orbit of n under this map, you get a strictly decreasing sequence for a while until it stabilizes in a number which has only 1 digit, which will be one of the digits in that base. Okay? So there's a minimum number, nu sub q of n, which tells you how long it takes until it stabilizes. And the question that was asked by Sloane is the following. I mean, he didn't formulate it as a conjecture, he formulated it as a question. Is this number, minimum number of steps, uniformly bounded in n? Okay, so that's the persistence problem. So here's the formulation. So is there a constant b, which may depend on the base q, but is otherwise independent of n, with the property that this number, nu sub q of n, is always less than or equal to b? Okay? This number is called the persistence of n. This nu sub q of n is the persistence of n. So the question is the persistence uniformly bounded in n? Okay? This is open. This has been open since 1973. It seems very kind of trivial question to ask, but okay. So in some sense, this problem, I mean, there are some serious undertones to it, and there's some relationship to the so-called Collatz problem, which you may have heard of. I mean, I think you've heard of. So it's the famous 3x plus 1 problem. If you take an integer, positive integer, if it's even, you divide by 2. If it's odd, you multiply by 3 and add 1, and you keep doing that. And the Collat's conjecture is that you always end up in the cycle 421, 421, 421, 421. And this has been open for even longer. This has been open for more than 80 years. Okay? This problem was popularized by Erdős. There is a relationship between this problem and that problem, but to explain the relationship, it would take me maybe too long. So the persistence is this number, nu sub q of n. And my purpose in this talk is just to show you how one can use some ideas from dynamics, more specifically from ergodic theory, to address this problem. But we're not going to solve the problem. So I don't have, unlike many of the speakers here, like some of the speakers this morning, I don't have any deep results to report here. They're just like simple, maybe simple observations. I hope that some of them are non-trivial. So let me start giving you some examples. So first of all, in base 2, there is absolutely no fun in this problem, right? Because if you take a number and you write it in base 2, you will have a string of 1s and 0s. If there is a 0 somewhere, the product is already 0 and the process stops. If you don't have a 0, you only have 1s, the product is 1 and the process also stops. So this means that every number has persistence 1 in base 2. So the question asked by Sloane has a positive answer in that case. Okay? So it's no fun. But as soon as you go to a higher base, like base 3, the problem is already open. Okay? In fact, in base 3, no number with persistence greater than 3 has ever been found. I'll show you later a number that has persistence exactly equal to 3. Okay? So after 3 steps, it stabilizes. So let's look at the original problem in base 10, which was the one that Sloane formulated. So here's a number that has persistence 7. So this number is 68,889. If you multiply the digits together, I think it's here, yeah? So you multiply the digits of this guy, you get this guy. You multiply the digits of this guy, you get this guy, and so on, until you reach 0. So you reach 0 after 7 steps. Okay? So there are numbers with seemingly large persistence. 7 is large for me. But there is even larger one. So this number here, for instance. Oops. This number, which I will not attempt to say in English. I don't even know if I can say it in Portuguese. This has persistence 11. I'll let you do the calculations. After 11 steps, you reach a single-digit number. Okay? No number with persistence larger than 11 has ever been found in base 10. This is completely open. Okay? And when I say that, I should quantify. This has been checked for all n up to this number. And in fact, even a bit larger than that if you think about it. Because if you add, if you take 10 to the 233 and you add 10 to the 234 to it, to all of these numbers, you get something that cannot have any higher persistence than you already had. Okay? So that's the problem. So what can we say about this problem? So part of what I'm going to say here is that we have like a probabilistic version of this of this problem. Okay, we will show that most numbers, in some sense, have persistence less than or equal to 2. Now, let me try to quantify this. Most numbers, if you fix any base, of course, most numbers in the sense of density will have at least 1 0 in their base Q representation. So most numbers have persistence 1. So I'm not talking about those. I'm talking about the ones that when you calculate the persistence the first time, you get something which is, when you calculate the product the first time, you get something which is non-zero. Okay? Then among those numbers, we're going to show that a very rarefied subset could have persistence, could have the value of the Sloane map applied to them could be non-zero. Okay? So, and I will focus mostly on base Q equals 3, but a lot of what I'm going to say is for all bases. So, if you look at base 3 is simple because of the following. well, either when you write the number in base 3, either you have a 0 and then the Sloane map applied to that number is 0, or you have a number which has only 1s and 2s, so when you apply the Sloane map, you get a power of 2. So it suffices to look at what happens with powers of 2. So if you knew that only finitely many powers of 2 don't have any zeros in their base 3 representation, you would solve this problem in base 3. Okay? But no one knows that. So that's, in fact, conjecture. So here's the conjecture. There is a moment after which all powers of 2 to the k, exhibit at least 1 0 in their base 3 representation. Now, Charles and I have a very strong form of this conjecture. Our conjecture is that the digits of these powers of 2, they become more or less uniformly distributed as you increase the power. Okay? You see as many zeros as you see 1s and as you see 2s in the base 3 representation. You'll see that in a moment when I'll show you a nice colored table. So there's a lot of computational evidence in favor of this conjecture, and this conjecture, of course, would only solve the persistence problem in base 3. Yeah? Okay, so here's a simple table. So here are the powers of 2 up to 2 to the 17th written in base 3. And as you can see here, some of them don't have any zeros, like this one, this one, this one, this one. And then you have to search carefully, and you only find this one. This one is the highest power of 2 that has ever been found with no zeros in its base 3 representation. Okay? So this provides you with an example of persistence 3, because the persistence of this number is actually 2. Because if you multiply the digits of this guy, you get 2 to the 6th. So if you go to the table here, 2 to the 6 is 2101, and you already jump to 0 at the next step. Okay? So after 2 steps, you're at 0. So the persistence of this guy is 2. So if you take the number 3 to the 16 minus 1, take this number, and you write it in base 3, you see a bunch of 2s. You see 15 2s here. Okay? So this number, the product of its digits is given by that number, and that number has persistence 2, so this one has persistence 3. And no one has ever found a number with persistence higher than that in base 3. Okay? All right, so I'm going to skip a few things here. So there's a little bit of stuff that you can do with elementary arithmetic. Okay? So for instance, you would like to show that this function I just defined earlier, nu sub q of n, that it is bounded. So you can't quite do that, so you do the next best thing. You show that it actually grows very slowly. So it's possible to show that the growth of nu sub q of n is at most like log n. Okay? And this follows from a simple lemma in arithmetic. It uses like an easy version of Catalan's conjecture. So if you have a number which is a power of 2, and you write it in base 3, then at least one of its digits has to be different from 2. Okay? They cannot be all equal to 2. Because if they were all equal to 2, they would be of the form 3 to the n minus 1. So you would have a power of 2, which is like 3 to the n minus 1, so you would have a solution to Catalan's equation. And there are no solutions to Catalan's equation except the obvious one, which is 2 to the 3 minus 3 squared is equal to 1. Okay? Or the other way around. 3 squared minus 2 to the 3 is equal to 1. Anyway, so from that you get an estimate on the Sloane map for powers of 2, and from that you actually get a bound like the one I said. The persistence in base 3 grows at most like a constant times log n. Okay? Anyway, I'm not going to go into that. Another thing I would like to just mention. There are some patterns in this table that maybe you may have noticed. So if you look at the last digit, you see 1, 2, 1, 2, 1, 2. So it's a periodic sequence of period 2. If you look at the last 2 digits, you see, if you put a 0 here, see 0, 1, 0, 2, 1, 1, 2, 2, 2, 1, 1, 2, and then it starts repeating. 0, 1, 0, 2, 1, 2, sorry, 1, 1, 2, 2, and so forth. So it has period 6. If you look at the last 3 digits, you see period 18. If you look at the last 4 digits, you see period 54. So you always multiply by 3. So the last k digits have period 2 times 3 to the k minus 1. That's something you can prove using Euler's totient function. That's not difficult to do. And it just follows from the basic arithmetic fact that 2 is a primitive root modulo 3 to the k for every k. Okay? So I'm not going to do any of that. So I'm going to skip this arithmetic. It's just like curiosity. But, it's just showing that you can prove some stuff about it, some patterns about it. And you can actually do something more general. You can look at the residues of p to the n mod q for any q. And you have some periodicity there, and you can compute the period using Euler's totient function. So in particular, you get this result I just mentioned to you, that the last k digits of 2 to the n in base 3 have they exhibit this periodic behavior. Okay? All right. So what I really want to talk about is another part of that table, which is looking at the heads, not at the tails, but looking at the first few digits, not the last few digits. That sequence is no longer periodic, but it's almost periodic. Okay? And that's where the dynamics comes in. So, see this, let me go back to the table just for a moment. So here's an idea. This is where Charles Tresser is very good at looking at these things and suggesting something. So he looked at this and said, why don't we put a decimal point in front of all of these numbers? They're growing, so let's make them not grow. Let's make them stay between 0 and 1. So you just put a decimal point in front of each one of them. And then, voila, they become the orbit of a certain map on the interval 0, 1, which is actually not really the interval 0, 1. It's the interval that goes from 1 over q, or 1/3, to 1. Okay? So let me define this map for you. So, okay. So I'm saying is, let me do something more general, slightly more general. So, sorry. So let's look at the, let's fix 2 integers, p and q, and let's write p to the n in base q. So you write the expansion. The number of digits is given by this formula. So the key idea is to add a decimal point in front of this expression. So what does that mean? That means taking this number and dividing by q to this power to shift all the digits after the decimal point. So you get these xn's here. Okay, I'm dividing p to the n by q to the k sub n, where k sub n is exactly the number of digits I have here. So I get a number which lies in this interval here from 1 over q, where q is the base, and 1. Okay? This sequence, xn, turns out to be the orbit of this map. So define a map. You define a map from this interval, delta sub q, I just defined, to itself, like that. So it's you multiply by p when you can, until you don't go over 1. If you go over 1, you have to divide by q also. So you get the following figure. So it's a piecewise affine map of this interval, delta sub q. And here's the picture. So it's built out of 2 linear maps. You see an expanding map here and a contracting map here. But the interval that we're interested in is not 0, 1. It's just the interval that goes from 1 over q to 1. So you have a self-map of this interval. So in fact, if you glue this guy to this guy, you get a circle, and you get a circle map there. It's a piecewise affine map of a circle. And what is nice about this map? So what is that sequence x sub n I just defined to you? It's precisely the orbit of this point here, 1 over q, under this map. Okay? And it turns out that this map, you can say everything you want about this map. This piecewise linear map is topologically conjugate to a rotation. And you can calculate the rotation number. The rotation number is just the log of p in base q. Okay? And you can, in fact, see that there is an absolutely continuous invariant measure. And I want to point out the important thing here. Notice that the expression for the measure, for the density of this measure, depends only on q and not on p. This will be very important later when I generalize the problem to bases greater than 3. Okay? So for instance, if you're working with base 3, the rotation number is log 2 in base 3. Right? Okay. So all orbits are dense. This map is uniquely ergodic. This map is uniquely ergodic. And that's very nice because you're just studying one orbit of this map. And you would like to say that this orbit is kind of typical. In general, you don't know if one orbit that you're studying is typical. But if your system is uniquely ergodic, then every orbit is typical. So you can say something about that, right? Well, I'll skip the proof, okay? So the proof is very elementary. But the point is that you can actually write explicitly the conjugacy between the rotation and our map. And the conjugacy is actually smooth at all points except one on the circle. It's in fact even Rio analytic at all points except one. So, you can say everything. You can, using the derivative of this map H sub t, you get an expression for the density. You just do some little calculation and you get the density is given by what I told you that it was, which is this, okay? So I'm going to skip the proof, otherwise I don't really get to the end of this. So what are the consequences, arithmetic consequences, the fact that you have this dynamics? So I'll give you two consequences. One is completely, it's nice to look at and so on, but it's completely useless. The second is a probabilistic version of Sloane for base 3, which is the thing I was telling you about. So the first corollary is that when you look at that table of powers of 2, and I'll give you a longer table in a moment, if you look at that table of powers of 2 and you look at the expansions in base 3, you have a formula to tell each digit in that table. If I give you, and if I ask you, what is the 10th digit from the left on the line 800? You can tell me exactly what it is if you can do this calculation, if you can do this. Okay? So you might say, well, wait a minute, we want to find zeros, right? And we would like to show that every line after a certain point has at least one zero in this base 3 expansion. Yeah? If we could do that, we would solve the Sloane problem in base 3. So why can't we just use this formula to get zeros or something? Well, there is a problem with this formula. You see this alpha here. What is alpha? Alpha is the log of 2 in base 3. It's a rotation number. This alpha, if you want to calculate n alpha and take the fractional part of that, to be able to calculate that precisely, you need to know alpha to a very large precision. And you would even be able to do that if you knew something about the continued fraction expansion of alpha. Unfortunately, these numbers, no one knows anything theoretically about log of p in base q in general. Okay? There are some algorithms for computing these coefficients of the continued fraction expansion in this case, fast algorithms, but they don't give you any insight on the theory, what they are. So this formula is an illusion. What? Yeah. I don't think that these numbers are bounded type. There is a guy called Shanks. I think it's Donald Shanks, his name. He's a computational number theorist. He has worked out an algorithm for calculating log of p in base q for various values of p and q. He has an algorithm that works for all p and q's, actually. But the algorithm, when you start computing it with some numbers, you see that these ANs of the continued fraction, they stay very small for a while, and then all of a sudden, they jump to very large numbers. So most likely, they are not bounded type. But not even that is known, as far as... I think we have a master on these things here. Google may know more about that than anyone. So the formula is really useless. If it was something like bounded type, maybe. But if it grows too fast or something, then I have no idea. Like a Liouville, yeah, exactly. Anyway, there are some results about Diophantine approximations of these numbers, but that's another issue. So anyway, that's a useless formula. So it's not really interesting. But I just gave you as a curiosity. Now, this corollary of the mere existence of that map with that invariant measure, the unique ergodicity, and so on, allows you to conclude that the Sloane problem has a positive answer in a probabilistic sense here. If you just look at the powers of 2, it is extremely rare for a power of 2 not to have a 0. That's what this thing is saying. Okay? The set of n's for which this thing is equal to 0, in other words, for which the base 3 representation of 2 to the n has a 0, this set has density 1. So for very few n's, 2 to the n will not have a 0. This doesn't solve the problem, because the problem would require us to prove that only finitely many powers don't have zeros, okay, in base 3. Okay, powers of 2, yeah? Both theorems, both corollaries, sorry, they follow from the unique ergodicity if you apply Birkhoff's ergodic theorem, so I'm not going to go into that. So let me give you a nicer table. Yes, so first let me ask, so some of the aims would be, you see, you have a periodic behavior for the last few digits of these powers of 2 on the right side, and you also have some almost periodic behavior on the left. So maybe you can combine these two behaviors to deduce what you want. You see, you know that on this side you have periodically lots of zeros, because on these last k digits, there are lots of situations where you have zeros, and you know more and more situations where you have zeros. So you have zeros here, and they appear periodically. And on this side, you have something which is almost periodic. So maybe the conjunction of something which is periodic on one side and almost periodic on the other, maybe it will lead to a proof. I don't know. We haven't been able to do that. But we observe that there is a stronger thing happening there. That on average, as you go along this table and you look at these digits, you see that they become kind of balanced. You have as many zeros as you have ones as you have twos. That was not so visible in the table I've given you, but maybe it's a little bit more visible on this table. These colors are, well, it's okay. So you see, it's the same table I had given you, so, except that we now go way down. 16 here really means 2 to the 15. It's because stupidly we didn't start with 0 here. We started with 1, but you know, that's... Anyway, so that was the last power of 2 that didn't have any zeros in its base 3 representation. If you look at these, if you look at this diagram from a distance, you see some things that look a little bit like, you know, a Sierpinski gasket of sorts, except that it's a little bit perturbed by the effect of carryover. This is the whole problem here, is that you have this carryover effect when you multiply. From each line to the next, you're multiplying by 2, and there is a carryover effect on these operations. So this perturbs this picture. So it's not a nice Sierpinski gasket, but it's kind of trying to be one. Yeah? So for instance, you see here lots of 2's, and then a little bit less. So this is like a little bit like a triangle here, a triangle here. There's also a triangle of zeros and so on. And I don't know if you noticed this, but if you look at the last line here, 2 to the 44, this power here, if you count, you know, how many 2's you have, how many 1's you have, how many zeros you have, you see that you have more or less the same number already. Okay? We have tested this up to 2 to the 7,000. And the frequency, sorry. Each digit appears 1/3 of the time, the proportion on each line. Yeah? So this is what I wrote here, see? The average number of digits equal to d, for any d equal to 0, 1, and 2 is 1/3. So this means that in each line, as you go along, the frequencies are converging to 1/3. Yeah? The previous corollary just says that there is some, that in most lines there is at least a 0.
Yeah, but can you say that how fast?
No, unless you're able to do some kind of Birkhoff theorem with a remainder, because you just apply Birkhoff's theorem. Yeah. I mean, you use the fact that it's uniquely ergodic, and then you apply Birkhoff. So it's yeah. Anyway, so I was going to actually show you another picture. I don't know if I can do that. I think it's Alt-Tab. Oops, yeah. So what is this picture of? This is You see, this is accumulating on 1/3. So this is going up to 2 to the 7,000. We are counting how many zeros we see in the representation and dividing by the total number of digits in that representation. And this is sort of, you can see that it's converging to 1/3. But it's converging kind of slowly. It's not really converging very fast, okay? So I don't know about remainers. Let's see, how do I get back to that? I do this. Yeah, okay, good. So, you have a better... Right. But I mean, the problem is that we don't know the Diophantine properties of these numbers. So, I mean, not... at least I haven't... Right. If you use... Right. If you could use something like Dangerois-Coxma. You're right. Yeah. Anyway. But, you know, since we don't really... I mean, we haven't really attempted to do that because we don't really have a... Anyway. So, what about other bases? I'm just talking about base 3. So suppose I want to analyze this problem in other bases, including the original problem, which is base 10. So then it turns out that you cannot really encode what's happening by just one transformation of the circle. You need to use several transformations of the circle, several piecewise affine maps of the circle, and they form an abelian group. Okay? So let me look at the primes between 2 and q minus 1. Q is the base. Yeah. So then the Sloane map. If you take a non-negative integer and you apply the Sloane map to this integer, and suppose it's not 0. If it's 0, the process stops already, so you don't have to do anything. If it's non-zero, then you can write the value of the Sloane map like that, as a product of powers of these primes. Because remember that the SQ of n is the product of the digits of n in base q. So since each digit can be written as a prime in that range, you get a product like that. Okay? So now what Charles and I are able to show is that, in some sense that you see in a moment, is that for most of these m tuples of numbers here, if you apply the Sloane map again to this product, you get 0. Okay? So in a probabilistic sense, again, the persistence of almost every number in base q is going to be 2, at most 2. Okay? So, so you need to consider, remember the maps TPQ I had defined, yeah? So let me write quickly here. So TPQ of x was equal to px if x is in the interval from 1 over q to 1 over p. Close here. And it's px over q if x is in the interval that goes from 1 over p to 1. Okay? So you fix q. Q is fixed. But now you look at TPIQ, where the PIs are these primes that you see here. So these guys generate a group. Remember, I had given you a result that showed that TPQ preserves a certain measure with a density that depended only on Q but not on P, right? So all of these maps for the fixed Q and P varying in P1, P2, Pm, all of these preserve the same measure. So they are all conjugate to rotations by the same homeomorphism. And since the rotations commute, these transformations commute. So these transformations form an abelian group. Okay? So you have an abelian action on the circle. So now you can use a little bit of ergodic theory of abelian action. So let me just make a digression. So I'll denote PL plus the group of piecewise linear, orientation-preserving piecewise linear maps of the homeomorphisms of this interval, delta. So first thing is that this group, so what is this group? The group is the group generated by these transformations here. Okay? So this group, G sub Q, is abelian. So this is what I just told you. So in particular, this means that you have a representation of Zm in this in the group of piecewise affine homeomorphisms of delta sub q. That's just the homomorphism. But this homomorphism is not necessarily, so this representation is not faithful because, for instance, let me give you an example. Suppose you have base 10. So if you're working in base 10, 10 is 2 times 5. So you can look at T2, 10 and T5, 10. The rotation number of this one is log 2 in base 10. The rotation number of this one is log 5 in base 10. The sum of these two rotation numbers is 1. So this means these maps are actually inverse to each other. It's not, and it's easy to actually see this directly. Okay? So there is a relation in these generators. Composition of these two is the identity. So that's not, okay? So it's not a free action. Okay? But so first of all, what is the relevance of this action for the Sloane map, right? So the reason why this is relevant is that the entire range of values that the Sloane map assumes in base Q, except for 0. If you exclude the numbers that have 0 right away when you apply the Sloane map first time, the non-zero values are precisely given by the guys that appear in a single orbit of a point in the circle by this action, okay, by this lattice. In fact, just by the positive lattice. You just iterate the semi-group. You're not interested in the whole group, just the semi-group, okay? So, and the reason is because if you take the point 1 over q, which is the left-hand point of that interval, and you apply these various maps, what you get is this. So it's just products of this type, okay, which are values of the Sloane map divided by enough powers of q to shift everything to become less than 1. Okay. So this K sub n is actually computable. It's given by this formula, but this doesn't really matter. So let me just make a few remarks about general, abelian actions on the circle, free abelian actions. So it's just in order to state something which is a criterion for unique ergodicity. Because we're talking about one orbit of a dynamical system, and we need to say something that implies that this orbit is typical. And this thing is unique ergodicity. So if you have a free abelian group of rank K with a certain set of generators, you can define, you take any element of the group, there's a unique expression of this element as a sum of a linear combination of the generators. So I'll denote by norm of G the maximum of these integers in absolute value. That's a norm in this group. And I'm just going to look actually at the semi-group because I'm only iterating forwards. Okay. And let me denote for each n, positive integer n or non-negative integer n, I define this guy to be the cube. So this is like a cube in your lattice. Okay. The set of elements that have norm less than or equal to n. And I define the appropriate object for the semi-group. So if you're in Z2, for instance, in Z2, these are like squares. So your lambda sub n's, they look like that. Okay, and the lambda sub n's plus, they look like that. Okay? Where here is like n. Okay, I mean just the integer coordinates, of course. So anyway, so this is just notation in order to state the following. So now suppose that this group, this abelian group, acts on some probability measured space as a group of measure preserving transformations. Then you have so that's just explaining that. So then you have a version of, you can define the concept of ergodicity in the same way, right? I mean, the action is ergodic if the only measurable sets which are invariant under the elements of a group are either null sets or full measure sets. So you have a version of Birkhoff's ergodic theorem. So I'm sorry I'm going a bit quickly here, but so you have a multidimensional version of Birkhoff's theorem. This is well known, right? So this is saying that the time averages converge to the space average. except that time now is like multidimensional time, right? But still discrete. And you can also define the concept of unique ergodicity. So just like the case where you have only one transformation. This is the same definition. So if you have a G action or a G plus action on a compact metric space by continuous maps, it's uniquely ergodic if there exists a unique Borel probability measure, which is G invariant. And there's a criterion for unique ergodicity, which is just like the one for rank 1 maps, okay? For rank 1 actions. So if I'll just state, it's actually if and only if, but I'll just state the direction I'm going to use. So if you have a G plus action by continuous maps on a compact metric space, and it's uniquely ergodic, then for every continuous function on this metric space, the convergence of the time averages to the space average is uniform. That's a well-known criterion, right? Anyway, it happens to be if and only if, but anyway. So now remember that I told you that that group G sub Q generated by all the TPI Qs and so on, this was not really a free abelian group. It had some relations in general. But let's look at some subset of generators. And I'll denote the group generated by those guys by that. These are the indices that I choose between 1 and m. M is the number of primes between 1 and the base. So if you look at this subgroup, and recall that each one of these TPIs, I'm denoting TPI instead of TPIQ because the Q is fixed. Okay? So these TPIs, they have these rotation numbers. So suppose that these rotation numbers are rationally independent when you add 1. Adding 1 means that each one of them has to be irrational also. Okay? So what are the cases I'm disregarding here? I'm disregarding the situation where you have the base Q and your P is such that Q is a power of P. That's bad. Okay? Like for instance, if you're in base 4 and you're looking at 2. 2 squared is equal to 4. So what happens is that every time you see 2 2's in your product for the value of the Sloane map, this means that you have already a 0 in the base 4 representation, so it goes away. Okay? So I'm excluding this situation. So let's look at these TPIs and assume that these numbers are rationally independent. Okay? Then you have a free abelian group. Okay? And its action is uniquely ergodic. Why is it uniquely ergodic? Because each one of these maps is conjugate to an irrational rotation by the same homeomorphism, which is smooth at all points except 1. So there's only one invariant measure. Okay? Each one of them is already uniquely ergodic, so the entire group action is uniquely ergodic. So what is the relevance of this result for the Sloane map? It's the analog of the result I had told you about base 3. It's telling you that very rarely the second iterate of the Sloane map will be non-zero. For most values that you pick, if you look at these guys, look at these numbers here. These numbers are values of the Sloane map when you apply it to any natural number that you pick. Either you get a 0 or you get a number that looks like that. Okay? So I'm saying that the very next iterate is already 0 with very high probability. For a subset of this lattice, the positive lattice, with density 1. The density is defined in the same way as you define in dimension 1. Okay? So that's the theorem. And it's not a difficult theorem, but uses the unique ergodicity, of course. And it gives a quantitative meaning to this assertion I made in the beginning that most positive integers n have persistence less than or equal to 2 and base q. Okay? Now, okay, so it's nothing really deep. But now I'd like to generalize this whole thing. So it turns out that Charles and I have a conjecture which is more general. And it concerns a game that you can play, which we call a multiplication automaton. So it's going to be similar, but different, from a cellular automaton, from a one-dimensional cellular automaton. So what is the game that you can play? The game is like this. You start with a positive number of your choice, integer. and then you choose some multipliers from a given set of multipliers. And then you start multiplying. So you take your number, multiply by the first guy you see on the list, then multiply by the second, then by the third, and you kind of write all of these numbers in a certain base Q. So these are all sequences of symbols from a finite alphabet with Q symbols. Yeah? And you start looking at the evolution of this. This is like an automaton. And the conjecture is that this evolution leads to an equilibrium. It goes to a situation where all the symbols are more or less uniformly distributed. Okay? So let me give you a formal definition, just in a statement. So I'll choose a base, fix a base, and I choose a finite set of primes with the property that not all the prime divisors of the base are in the set. For instance, if it's base 10, I could have like 2, 7, and 13, for instance. But I don't want to have 2 and 5 at the same time in the set. Why not? Because when I multiply 2 times 5, I get a 0 already. And if I keep multiplying by 2 and by 5, I start getting more and more zeros. And there's no hope of having uniform distribution of digits like the one I'm suggesting. So not all prime divisors of the base should be in this set F. So we call this an allowable set of primes for this base Q. And you play the game I just described to you. So you start with a positive integer A, and then you randomly select elements from the set F. So you go there and you draw a first one, pi 1, put it back. Then pi 2, then pi 3, and so on. Okay? So you have a sequence of numbers chosen from this finite set F. And then you build these numbers just by multiplying like that. So the conjecture is that as you go along and you look at the base Q representation of these numbers, the frequency with which you see a given digit approaches 1 over Q. And more than that, same thing is valid for blocks of any length. If you fix any block of digits and you search how many times that block appears in the number n sub n, count how many blocks you have, divide by the total number of blocks, let the n go to infinity, it converges to the right proportion of blocks that you would expect. Yes? There's no need for a measure here because I'm not making a probabilistic statement on F. I'm just, okay? Yeah, but I'm saying that for every choice, something happens. Not for almost every choice, but for every choice. Okay? Okay, so here's the formal statement of what a multiplication automaton is. A multiplication automaton is just a configuration, an array of numbers with two maps. There's a configuration map. So this is telling you that it's a configuration on this quadrant in the lattice, Z2. And there is also something which is the carryover map, because the way you go from one line to the next is by multiplication by these multipliers. But you have to remember that there's always a carryover effect. So there's also a carryover map. So the way the digits are computed from one line to the next is by a formula like that, where you have to take into account that there is a carryover. And the carryover is also given recursively. Okay? So anyway, that's the definition of a multiplication automaton. I'll give you a couple of examples in a moment. So here's the conjecture I just mentioned. If you look at what happens as this automaton evolves, and you look at fix a block of a given length, the frequency with which this block appears in this automaton, in the line-by-line evolution of the automaton, is asymptotically given by 1 over Q to the L. Q to the L is the number of blocks that you have a length L in Q symbols. Okay? So that's the conjecture. And we have, so I'm not telling you the most interesting part of the paper maybe here, which is like a heuristic argument. At the end of the paper, we have an heuristic argument, not just the computational evidence, but we have an heuristic argument which uses the theory of inhomogeneous Markov chains to show that this is a reasonable thing to expect. But we don't have a proof. It seems that we almost have a proof, but we can't really claim we have a proof. Okay? So, for instance, simplest example is the table I had given you before, because if you fix the base to be Q equals 3, and if your allowable set of primes is just formed by the prime 2, then this means that, and you start with a seed A equals 1, this means you start with 1 and you're just multiplying by 2, so you get all the powers of 2. Okay, and you write them in base 3. But here's another example. So let's see. Yeah, so this is just explaining why this falls in the previous framework. So let me give you another example. Another example is base 4. If you take base 4 and you choose the set F to be just the prime 3, and the initial sequence of carryovers is 0, I'm not going to talk about that, then what you get is, if you choose A equals 1, you get the sequence of powers of 3, written in base 4. If you choose A equals 2, you have the sequence 2 times 3 to the n in base 4. So these are given in the following picture. Okay? So here you see, on this side you see the powers of 3 in base 4, and here you see their doubles, I hope. Yeah, see? And again, you see some patterns. If you know, there are only 24 lines on this automaton, so you can't quite see the uniform distribution yet. You know, you see if you count how many ones you have, how many twos you have, how many zeros. You see that there's too few zeros. There's only 2 zeros here. There's only 2 zeros here. This is because it's still too early to see the uniform distribution. But believe me, we have these tables. Charles has written program with like thousands of lines, and it's just okay. So now, why does the set F need to be finite? So I'll end by doing this little kind of Olympiad kind of observation, Olympiad problem kind of observation. The set F in this conjecture needs to be finite. If it's infinite, the conjecture is false because of the following thing that I found. This is very simple. So recall what a repunit is. This is not a very conventional thing. A repunit is a natural number that in a given base can be written as only with the digit 1 many times. Okay, like 1, 11, 111. So let me work with base 10 just to fix ideas. But the same thing I'm doing here works in any base. So a repunit is a number that can be written like that. Okay? If it has n numbers equal to 1, it's written like that. Okay, good. So now take the following sequence of repunits. You choose the repunits R1, R2, and so on. Not the way I defined before, but using 2 to the n here, see? So this is a number that has 2 to the n once in its base 10 expansion. Okay? Now, the point is that you have this factorization here. So this means that each one of these guys is a multiple of the previous one. And what you see on this side is relatively prime to what you see on this side, because these are both odd numbers, and the only factors, if they had a common factor, the common factor would divide the difference between them, which is 2. So it cannot be. So this guy is relatively prime with this one. So what this means is that these numbers, they go like, each one is a multiple of the next one, I mean of the previous one, and each time you introduce a prime that was not in the list before. This guy has a prime divisor that is not a prime divisor of any one of the numbers that came before on the list. Okay? But now clearly, they are appearing in some automaton, in a multiplication automaton, if you allow the set F to be infinite. Because you just take the set of the sequence of primes that appears in these R1, R2, and so on. Okay? So like, for instance, R1. What is R1? R1 is 10 squared minus 1 over 9, which is 11. So that's your first prime, 11. Then you go to the next one. The next one, you have to find a prime of 10 to the 2 squared plus 1. So 101. So 101 happens to be prime. So that's your next prime, and so on. Okay? So you get an infinite sequence of primes, and each one of these Rn's is a product of some of these primes. So these Rn's, they appear in the line-by-line evolution of some automaton, if you allow the set F to be infinite. So this fails the conjecture, because this means that from time to time you find a line made out only of ones. You cannot have equidistribution of digits in that case. Okay? So that's why F needs to be finite, for the conjecture to have some hope of being true. And what I'm saying is that we have some heuristic argument for the conjecture, but we don't have a